Hi, I'm Nico from the University of Potsdam, and I'm going to talk about a Bayesian ground motion model for estimating the covariance structure of ground motion intensity parameters. And just for an introduction, you probably all know that ground motion models are very important for probabilistic seismic hazard analysis. And for ground motion model, we usually assume that the logarithm of some ground motion parameter, for example PGA or PGV, is distributed normally with a certain mean, which is a function of some predictor variables such as magnitude, distance, VS30, focal mechanism, and standard deviation sigma. And in the following we will call the logarithm of our ground motion parameter, we will call that Z. And this representation of a ground motion model, of course, neglects that different ground motion intensity parameters are actually not independent. They are correlated. For example, if PGA is large, we assume or we expect that probably PGV is also large. And another issue in this context is that there's of course a lot of uncertainty, which is in the function parameters, in the function itself, in the predictor variables, and we're going to try to address some of these issues. And for the first one, we're just going to extend the simple multivariate model right here to the simple univariate model to a multivariate model, where we now assume we have a vector of ground motion intensity parameters which are distributed according to a multivariate normal distribution with a vector of means which are functions of the predictor variables and the covariance matrix sigma. And then we are also, to address uncertainty, we're going to build a multi-level probabilistic graphical model. And graphical models are a huge and very flexible framework to address, to reason under uncertainty. And the multiple levels in our model allow us to deal with group data, for example, multiple recorded events, multiple recording sites. And the graphical model also allows, because it's graphical, allows intuitive insight into the model, and on a more semantical way, it allows us to factorize the joint distribution of data and parameters, which we can exploit later for learning. And then we're going to estimate the parameters of our model by Bayesian inference, which gives us a fully probabilistic interpretation of the parameters. Just a short introduction to Bayesian inference. We are interested in the distribution of the parameters given the data, and this can be calculated according to Bayes' rule, which we can see here. And this formula can be interpreted as having a prior distribution over the parameters which is updated given the likelihood of the data to yield the posterior distribution of the parameters given the data. And this is of course very nice, because here we have a principled way to include prior information over our parameters, which is then updated using the data. And this updating can be one at a time or using a whole batch of data. The prior information is quantified in terms of a probability distribution, and that means a number between 0 and 1. And that's of course also very nice, because it's a very principled way to do that. But of course sometimes it can be not so easy to specify a probability distribution over a certain parameter. And then the posterior distribution for simple models may be calculated analytically depending on the form of the likelihood and the prior, but for more complicated models we have to resort to approximate inference, and that's also what we're going to do here. The posterior distribution is estimated using Markov chain Monte Carlo sampling, and in particular Gibbs sampling. And Gibbs sampling makes use of the factorization of the joint distribution, which is also of course neat because the graphical structure of the model provides such a factorization. So now to build our model, we need to have a prior distribution over the prime. We need to have the model right here, and we need to have some data. Just a quick word for the data. We used the data set compiled by Allen and Walt to evaluate ground motion models for use in shake maps. We use about 8,000 records from 159 earthquakes, each of them from shallow active tectonics. There are 4 predictor variables and 5 target variables, and we're going to build a multivariate model for these targets given the predictors. Here shown is the magnitude distance distribution, and you can see that the data range is fairly well covered between magnitudes 5 and 8 and distances of about 10 to 400 kilometers. Now we'll come to the model, and this is a conceptual model or a graphical model. And in a graphical model, each quantity is represented as a node, and arcs between the node denote direct dependence between the nodes. There are different kinds of nodes. We have these white nodes here, which are stochastic nodes, and they are associated with the distribution. And we have these gray nodes, which are functional nodes, which means they are functions of other parameters or other quantities. Then we have these rectangular structures here, which are repetitive structures, basically loops. So for example, this one is a loop over the earthquakes, and this one is a loop over the stations, and that means and the intersection of these two is then the record, which is a record from one particular earthquake recorded at one particular station. And this model can be interpreted like this. We have our ground motion parameters recorded from one earthquake recorded at one station, which is sampled from a multivariate normal distribution with a particular mean and a covariance matrix, and the mean of that distribution is a function of 3 other quantities: an event term, a station term, and a record term. And the event term itself is again sampled from a multivariate normal distribution with a certain mean and a covariance matrix. The same is true for the station term, and the event term is common to each record from one particular earthquake, and the station term is common to each record recorded at one particular station. There's one thing: we don't consider the station variability, the between station variability, because we don't have a lot of stations which record multiple records, and therefore we cannot really estimate the covariance matrix in a stable way. This one corresponds to the between event covariance, and this one corresponds then to the within event covariance. The full graphical model looks like this. Now we have added parameters A, B, C, and our predictor variables moment, magnitude, distance, VS30, and the focal mechanism. And now the mean of the event term is a function of some parameters, focal mechanism and magnitude. The mean of the record term is a function of some parameters, the record, the distance, and of course the event term. And the same is true for the stations. You can see that the moment, magnitude, and distance are denoted as rectangular nodes, which means they are fully observed, while focal mechanism and VS30 are denoted as a stochastic node. And that is because we have some unknown data for these two predictor variables, but these unknown data are just treated as normal parameters of the model, which are associated with the distribution, and then we get the posterior distribution of the unknown predictor variables out of the model. It is very, very easy to extend such a model. If I had been able to come, I could have shown you my poster where we have extended this model to include also such a model to include also regional differences, where we just add another level for different regions. We could also include measurement uncertainties, for example, just associating each predictor variable with a distribution, and then sampling using Markov chain Monte Carlo sampling to estimate the posterior distribution. For each of the root nodes which have no parents, we need to specify a prior distribution. That means here for our parameters, for the covariances, and for the predictor variables. And that's of course sometimes not really easy. It's really difficult to quantify a probability distribution on individual parameters, and therefore we've chosen a different way. We have specified a distributions over stress drop and Q0, and then use stochastic simulations to obtain a synthetic data set from and then we have regressed our function on the synthetic data set, and then we use the regression estimates of these parameters the parameters as the prior distribution for our model. And now we'll come to the results. This is what it looks like. For each parameter theta, we have samples from its posterior distribution given the data. This is shown here for one particular parameter, which is used for magnitude scaling for PGA. Here we see we have a stable, good mixing posterior distribution, and here we have then a histogram of our posterior distribution, and then we can of course calculate the mean of this distribution. We can calculate quantiles in the interquartile range, or the maximum of this distribution. And the nice thing is it's a full probability distribution. The red line here is the prior, and we can see how the likelihood has moved our estimates of the parameter away from the prior. The same is true for the all covariance matrices, the between event covariance and the within event covariance. And we have used here we've plotted the probability distribution of PGV and PSA at 1 second. We've used the mean of the posterior distribution for their respected covariances, and as you can see, there's a lot of it's very different from an independent distribution. That means they are highly correlated. And what you can also see is that the between event shown in correlation shown in red is larger than the within event correlation. Here we've shown the joint distribution of PGA and PSA at 3 seconds, and you can see that there's still some correlation, but it's much less than in this case. All correlations are shown here. On the left side, the between event correlations, on the right side, the within event correlations, color coded from light colors to dark colors. Black is actually a correlation of 1. And you can see again that the between event correlation is larger and is larger than the within event correlation. That's basically all. I think I'm running out of time. We've seen, but that's of course not really new result, but we've seen that there are significant correlations between different ground motion intensity parameters. We've also seen that the between event correlation is larger than the within event correlation, and we can use the Bayesian formalism together with graphical models to make a fully probabilistic treatment of the uncertainty. And what we plan to do is also to include measurements, uncertainties on the predictor variables, and also to include different functional forms. We can just we can also directly calculate weights on functional forms using graphical models. That's all. If you have any questions, just email me, and I think I'm going to put the slides and also my poster, which I couldn't show, on my website. Thank you very much.